Okay, so any questions? Now, there are a lot of things I have not covered, so I'll have to just choose some, because today is the last lecture. So, I mean, there are many things which I have not covered here. So, did anyone try to read the chapter 13? Huh? Is it understandable?
Yes, I think.
It's just a straightforward calculation. I mean, choose a basis for the SUN, SON, SP, SPN, etc. Choose a basis for the kata and find the eigenvalues, the roots. So, I mean, is there any? Did anyone? I mean, anyone looked at chapter 13?
I did.
You did.
I did.
You did, and how do you find it?
It's fine. It repeats the same calculation over and over again.
Yeah.
You read the first part of the same.
That's same. But I mean, the important point is to understand the SUN, SON, SPN, etc., and not just SON, SO2n and SO2n plus 1. SO even and SO odd, they behave very differently. Well, I mean, somewhat differently, not exactly the same. So there's a distinction between them, SO2n and SO2n plus 1. And also SUN and SPN. So I mean, the main point, of course, the technique is simple. I mean, you just write down the algebra elements, choose a basis for the kata, and find the eigenfunctions. So all the roots, classify all the roots, so that's basically what it is, right? But it's important to go through it. There are a lot of exercises in that chapter, because as you're saying, the calculation is basically repetitive. I mean, once you have seen it in one context, then you can just do the same thing in the another context. Chapter 13, I'm talking about chapter 13. Right, but so a lot of things have been left as exercises. Unfortunately, I don't know what to cover now, because there are too many things to cover. There are too many things left over. Okay, but any questions from the last lecture? Right? So we had the notion of simple roots, and then we also introduced the notion of Ricotta matrix, right? So Ricotta matrix was defined as so if you have a rank n algebra, which means that this is the dimension of rank R, which is this is the dimension of the Ricotta subalgebra. Then we said that there are the simple roots. There exists R simple roots. Okay. Which we denote by alpha I going from 1 up to R. And the important property of this was that, among others, that if alpha I minus alpha j is not. I mean, if I look at any chain, so if I take two simple roots, alpha I and alpha j, right, then alpha I minus alpha j is not a root. So this way, what's happening is that if I consider so if I write down draw some alpha I and alpha j here, okay, then and look at the alpha I chain passing through the alpha j. So it will be like this here, right? Then alpha j minus alpha I does not exist. Okay, so it can only go positive. So alpha j plus alpha I, and so on. Right? So from this SU2 point of view, the SU2 defined by alpha I, this is a lowest weight state. Okay? And then this will form a representation. Okay? That depends on how far it goes. So in other words, we had this 2 alpha I, alpha j over alpha I was what we were calling P minus Q, which was which defined the chain, right? So this chain corresponded to alpha j plus say n alpha I, where n goes from minus P to Q, right? This was the thing. So since nothing exists, there's no negative ones, so what we are saying is that P is 0. So for these cases, for the simple roots, this is only for simple roots, not for other roots. For simple roots, this is the case, P is 0. And then it can only be positive. I mean, Q can be something. But then once you know this number, you know the number, since P is 0, it immediately tells you what is Q. Right? So you know how far this chain goes. Right? So for example, suppose Q was 4, minus Q was 4, then it will go, Q was 3, then it will go up to this point. Right? 1, 2, 3. So this will be a spin 3/2 representation. Right? From this SU2 point of view. Spin 3/2 is dimension 4. So this is for the P equal to 3, for Q equal to 3. You have that. If Q is equal to 2, you will not have this situation, but you will have it will stop at the 2, value 2. It will be spin 1 representation, and so on. And if Q equal to 1, then you have just one step. It stops there. Right? Set up. So by using these numbers, by having this information about the numbers, you can construct all the roots step by step. So here what I did, I looked at the alpha I chain passing through alpha j, but similarly you can ask what is the alpha j chain passing through alpha I, right? So keeping track of all of this information, you can construct all the roots of the system, of the particular algebra. Right? So essentially, so what we are saying is that these numbers encode all the information. So give me a set of roots. I mean, if I know if the rank is R, then there are R simple roots, right? And then you need to specify all these numbers. And once you have specified these numbers, then you can construct all the algebra, the complete algebra. Okay? So this is of course this is what we define Aij. I think we define the Ricotta matrix. Ricotta matrix exactly has all this information. Ricotta matrix is defined by some matrix A, which is a R cross R matrix, whose entry Aij was defined as 2 alpha I alpha j divided by alpha j alpha j. Okay. So this is the j. This is alpha j string passing through alpha I. Passing through alpha I. Okay. So if you specify all these numbers, these are all integers anyway, right? If you specify these numbers, then claim is that the algebra you can construct all the remaining roots, right? And therefore you know the algebra completely. Because once you have all the root structure, then you have the commutation relations, right? We already had what kind of a commutation relations you get. Okay, this is the important part. So basically, the information about the algebra is completely encoded in these numbers. So there is a way of writing. I mean, if I just give you these numbers, it's not very illuminating. I mean, it's easier to see it in a picture. So there is a graphical realization of way of writing down these numbers, and that is what is called the Dinkin diagram. At least to me, I mean, when I see this Dinkin diagram, it's easier to visualize because the picture. It's always easier to picture things. Linkage diagrams. So the idea of the linkage diagram is, so since if the rank is R, then you put R circles, small circles. So each circle represents a simple root. Okay. So let's say I have alpha 1, alpha 2, alpha 3, and so on. So these are the simple roots. These are simple roots. Not all the roots, just simple roots. So there are R of them.
Can you put them in any order?
At the moment, I just put them like that. Yeah. But now, so what is the? So where is the information coded here? We need this information, right? Now this we have seen that this can be only well, if I equal to j, then that's a trivial thing, right? If I look at the diagonal components a no sum involved, just a fixed a then you see that this cancels, right? So you just get 2. So diagonal is always 2. So the non-trivial information is the off-diagonal terms. 2 is always there. So what you do is that if I take, so for I not equal to j, this number, as we have seen before, that this can only be 3 minus 3, because these are for simple roots. This dot product is negative. So it can only be minus 3, minus 2, or minus 1. 0. The 4 is not, because we are thinking of this as distinct roots, right? So 4 would be the case only when they are parallel, parallel or anti-parallel. So you remove that, and so these numbers. So what you do is that if, let's suppose, for the 1, 2, the number is 3, then what you do is you put 3 lines. Okay. So you connect 2 roots, 2 simple roots, by these numbers. See. Yeah. Okay. So if this is 3, then you put 3 numbers. So this basically gives you information about the angle between the two. Remember, for these choices, what we have the numbers. The angles was 150 degrees. For this one was 135 degrees, and this one was 120 degrees. Right? These are obtuse angle because negative. So if it's 150 degrees, you put 3. So you put 3 lines here, the number of lines, and here you put 2 lines, and here you put 1 line. Okay. So this completely gives you the information about the dot products. Okay, that's one thing. The second information. Okay, so for example, let's suppose I have a thing where this is 120 degrees between alpha 2 and alpha 3. Between alpha 3 and alpha 2 is again 120 degrees. Okay, probably you might think that maybe there is also, if alpha 2 and alpha 4 dot product is not 0, then maybe there is also, say, some lines here. Right? So wherever, take pairwise these points, right? And look at the angle between these two. Okay, angles can only be one of these, or 0, of course. These are the only possible angles you can have. So if there is 0, that means you don't put any line, don't connect them. So this is the way. So that is one thing. But you see, when it is 120 degrees, then we know that the two lengths are the same of the roots, right? Remember if it's if Aij is 3. And so we had chosen Aij is equal to 3, minus 3, and Aj equal to minus 1. Remember the product, it was a product actually. In fact, I should really talk about the product here. The number of lines is the product, Aij, Aji. Okay? So this number of lines is the product Aij times Aji. That's right. So So if this is the case, then we also saw that one of them, I forget now which one it is, one of them, say I don't know, alpha j square is equal to 3 alpha I square. I may be making a mistake, maybe it's alpha I square, because we have exchanged. This was not n alpha beta. This is what we were calling n alpha j alpha I. So there has been an exchange. But anyway, one of them is going to be 3 times other. Right? If it is this number 3. So in the case of this 3, so now you have to also specify. So one of these roots is bigger, right? 3 times bigger. You don't have to specify 3 because that number is already here. No? Once you have specified this 3 here, 3 lines, then I know that the ratio, the length square of one of them will be 3 times the length square of the other, or vice versa. Right? So you need to have that information. And for that, now in the notes, we have chosen a convention which I don't like really. I don't really like that convention. The convention was, you put a solid, where is this? Deakin diagrams. Make the circle of shorter root solid. So in the notes, what one has done is that, let's suppose this root is shorter. One of them is longer, other is shorter. So the shorter root we fill it up, right? But you always forget which one, whether the solid is a shorter or solid is a longer, right? So to me, the much nicer way to write is longer. So let's say, so this length is bigger than that. This is bigger than or less than. Then it's unambiguous. You don't have to remember it. So, but the various books follow different.
That's standard convention.
Yeah, I think so. Yeah, that's you don't have to remember anything. It's already explicit. No. So this arrow would mean alpha 2 is bigger than alpha 1, or that arrow would mean alpha 1 is bigger than alpha 2. If there is a single line, there is nothing. You don't need to put any arrow because the lengths are the same. Okay. So when the number of lines is 3 or 2, that is when you have to put the arrow because the lengths are not the same. Okay, so this is it. This diagram captures all the information. You don't have to. Basically, it captures all the relevant information from the Ricotta matrix. This diagram. So looking at this diagram, you immediately know what it is. Now, this diagram is not always possible to draw. And not always possible. You cannot just choose arbitrarily. And not because of any very deep reason. It is simply that geometrically it is impossible in a Euclidean space. Okay. Just to give an example, let's suppose I can ask the question, and there are many things. This is just an example. An example. So, could I have something like this, a closed system? That you can show you cannot do that. For example, so let's take the simplest case. I have 3. There could be other things. I don't care. There could be other. But let's say there is some cycle inside. There could be many more points. But I'm just looking at some part of this. Could be some huge Deakin diagram. Okay, whatever. But could it be that there is some kind of a cycle inside there? And the answer is not. No, because if I put here, let me call it alpha 1, alpha 2, and alpha 3, then you see the fact that there are single lines, it tells you that angles between each of these 3 is 120 degrees. Right? So in particular, let's look at alpha 1 plus alpha 2 plus alpha 3 square. Right? Let's look at this. So what you find, you get here alpha 1 square, okay, plus alpha 2 square, plus alpha 3 square, minus 2 alpha 1 alpha 2, minus 2 alpha 1 alpha 3, minus 2 alpha 2. Right? I just open it up. Correct?
Plus.
Plus, okay, that's it. Now let us divide this by alpha 1 square. So what I get if I divide this whole thing by alpha 1 square, so you get here 1, but you see that the number of lines is 1, so this length is the same as that length, and also this line is 1, so this length is the same as that length. So all of these lengths are the same, so you get here 1 plus 1 plus 1, right? Because then I divide by alpha 1 square. Okay, now look at this here, 2 alpha 1 dot alpha 2 divided by alpha 1 square. Okay, that is going to be minus 1 because there's only one line, right? So this is minus 1. This also is minus 1, and this also, because here is alpha 1 square, but I know length is same, so I can replace it by alpha 2 square. Then this will be the corresponding A23, right? So also minus 1, so 0. Okay. So what does it mean? It means, on the other hand, we know the metric is positive definite, right? So that means this vector itself is 0, right? That means these are not linearly independent. But we have already seen that the simple roots are linearly independent, right? So this is impossible.
It's kind of like the HEP-LL rule that if we have a closed polygon, then the total force is 0, something like that.
Yeah.
If there's a closed polygon, then they will be linearly dependent because the sum scale is going to be 0.
Yeah, but I mean it's close polygon, but it's a very specific feature. I mean, you see, let's try to draw the picture. Alpha 1. Now I know alpha 2 is 120 degrees from here. Whatever. I mean, actually for this discussion, even the length doesn't matter. You know, the question is whether I can draw 3 lines, which are the property that is 120. So now I have to draw alpha 3, right?
But it's going to be in that plane. Therefore, it's going to be
precisely, right? So I mean, the one way to think about it, geometrically we can visualize it, is well, alpha 3 I have to draw, but alpha 3 should be 120 with respect to alpha 1 and 120 simultaneously with respect to alpha 2. Now think about it. So let me draw. So let's say this is 120. Okay. So if I draw but I mean, you see, this is already, once I make this 120, this is already in the one plane. Now, if I try to lift this, because suppose I want to, this has to be linearly independent, so it cannot be on this plane, right? If I try to lift it, angle will become less than 120, right? Because you see, if you look at this plane, right, and you try to lift it, it's not, I mean, angle will become less. In fact, on the opposite end, the angle is 60 degrees, right? So the 120 is if you look at this plane, the maximal angle is 120, and that happens only when it is in the plane. So all the 3 are in the same plane. This is what the statement is. The sum is in the same. I mean, 0 means that all 3 are in the same plane.
So can we have a cycle such that suppose that alpha 1 and alpha 2 have 2 lines between them?
No, even then you cannot. Even that's not possible. Yeah. Right. So, for example, let's suppose you are saying, let's say, consider put 2 lines here, right? Mm-hmm. That means alpha 1 and alpha 2 are 90 degrees, right? I mean, no, 2 lines 135 degrees, and I think in this case it's even impossible to draw any. I mean, not even in one plane. It's not even possible to do that.
So it means that any cycle is prohibited.
Any cycle is prohibited, yeah.
No matter how many lines you have.
Yeah. I mean, I have here done it only for 3, but you can do it for many. I mean, let's say. So you have alpha 4 also, right?
Okay, but no matter how many lines you have between those cycles are prohibited.
That's right. So no cycles, no closed cycles. So this way, similar thing. I mean, for example, another thing you can prove is that again, this is fun to try to prove this. It is purely Euclidean geometry, so you can try to prove various things. For example, if I have 3 lines between 2, and now I have another one, and here this simply cannot be connected. I mean, if it's connected by 1 line, 2 line, or 3 line, this is impossible. You cannot draw it. Okay. Again, you can try to prove it in a similar way. So that means if I have if I have a Dinkin diagram which contains 3 lines between 2 points, then that is it. There's nothing more. You cannot put anything else attached to it. Of course, you can have something disconnected from this. No, I mean you can have some diagrams like this, but that is not a simple algebra. That's semi-simple algebra, because this will the part of the algebra here will completely commute with the part of the algebra there. Okay, so that will be semi-simple. But if you restrict to simple algebras are those where the Dinkin diagrams are all connected. There is no, you cannot separate into 2 disconnected parts.
This is the G2 algebra, right?
This is G2. Yeah. The claim is that is the only thing. I mean, the only simple algebra which contains 3 lines is G2. There's nothing else. You cannot put anything more. Right? You try to prove that. I mean, it's rather quite instructive. It's fun actually. I mean, you can. Another thing you can try to prove is, for example, if I have a diagram like this with 2 consecutive things being with the double lines, again you can prove it's not possible. Okay. This is again the same thing. I mean, now because we are saying alpha 1, alpha 2 is 135 degrees, now I want to draw an alpha 3 which is 135 degrees with respect to that, and perpendicular with respect to alpha 1, because you see there is no line. So 1, 2 and 3, there is no line connecting that, right? So that means it's perpendicular. So alpha 3, whatever it is, should be in this plane, right? But but then you see the only possible, if you measure this angle on this plane, that's again 135. So once again, alpha 3 is forced to be in that plane, because if you can see, I mean, so okay, let's see. So I have, by drawing alpha 1 and alpha 2 like this, I have satisfied this condition, right? The fact that alpha 1 and alpha 3 are orthogonal, that means whatever the alpha 3 is, it should be in this plane. After all, there are 3 independent guys. I should be able to draw in 3-dimensional space, right? There are 3 vectors. I should be able to. So whatever it is, alpha 3 should be somewhere. So like that, or like this, or something, but lying on this plane, right? Alpha 3 should be some vector lying in this plane. But now, if you look at this, the 135 is coming when the alpha 3 is exactly in this plane. Right? Now try to lift this alpha 3 up all the way there. You see, angle between this and that is becoming lesser and lesser. No? I mean, you can picture it actually. So it's becoming lesser and lesser. So every other angle will be less than 135, except when this line is lying here. But then they are not linearly independent. No?
So when we try to prove the impossibility of a diagram, the generic situation that arises is that the roots will tend to be linearly dependent.
Or sometimes it's not even possible.
Not possible.
Yeah.
That's the only two.
Yeah, that's right. For example, take here. This would be even impossible on a plane, because this would mean its angle is 150, but the maximum is 135 here. No, so either it's impossible to draw altogether, or if it is possible, they are linearly dependent.
But if we replace these 3 lines by 1 line, then it is possible.
That's exactly. So if you have such a situation, then it's possible. Okay. And in fact, then you can keep going. There is no problem with this kind of single lines. There is no problem.
It's kind of like SUN.
These are SUN. Yeah, these are SUNs. So this is any number of points you can put in a single line. This has no problem. Geometrically, you can draw them. So the point is that wherever you can draw geometrically this root system, right? Simple root system, it is a allowed algebra. That's the statement. But this is allowed, right? But if you try to draw something something like this is not allowed.
How can I visualize the file?
Huh?
How can I visualize?
How you cannot visualize, but you can try to I mean, there are ways of doing it. One way is to, if you are lucky, linear dependence you can try to find by, like here we did, no? Like here. to prove linearly independent or not. But even more directly, because as I said, this issue does not even depend on the lengths of these guys. It is simply the ability to draw vectors with those angles. Lengths are not important.
Can we do that? Suppose that we have such kind of chain that the roots are connected by single lines, and suppose like that where you have drawn 5 circles. Then if we restrict ourselves to a subscale, then we can visualize it. Can we do that?
Yeah, but sometimes it's not possible. You see, for example, this is allowed. I mean, this is, it's not so, this is allowed. But if you add one more, either this way or that way, it doesn't matter, that's not allowed. But so it's difficult to visualize. But one way is to just start writing down some basis, and prove. Of course, it becomes impossible when you have large numbers, right?
But if you remove one, then is it possible or not? If you remove the last one?
Yeah, that's what I'm saying. This is possible. So if I remove this, that it becomes that.
No, from that one, if you remove one.
This is still possible. So in general, finally, I just give you the final answer. With 3 lines, and I'm looking at the simple, which means there are not 2 separate diagrams, 2 disconnected diagrams. So it's all connected diagrams. So 3 lines. The only possibility is this. There's nothing else. With the 2 lines, the only possibility is, for example, these types, and this number can be anything. There's no limit. These are all single lines. There's only one double line. This could be either this way or that way. I mean, I've not arrow just which root is bigger. No, so both are possible. This and this. Okay. Then the only other possibility with the 2 lines is this one here. I mean, so this is like these 2 lines are in the end of one of the chain. Think of this as a chain. Then both these diagrams are where the 2 lines appear at the end, one end of the thing, right? And then after that you can add any number of single lines. Okay. And here you have both these possibilities. Here, on the other hand, if you have 2 lines appearing not at the ends but in the middle, somewhere, then this is the only diagram which is possible. No, you cannot continue. No, this is all. And this is what is called the G2. This is what is called the F4. And here it doesn't matter, right? Because diagram is symmetric, so it doesn't matter whether you put the arrow this way or that way. That's just relabeling the roots, no, simple roots. Then you can also ask, can I have things like, I don't know, I have several points here, several simple roots here, and maybe I can have such a thing? No, not possible again. The only possibility is a three vertex. I mean a vertex like that. That's the only possibility. And here again you can draw. You can take from one of these, and you can keep going. Any numbers. No, it's indefinite. This is dn. Yeah. So dn. So I will come to that. So this is G2. This is F4. One of them. This is what is called Cn. N refers to the number of points. So actually, in our notation is CR. R is a rank, let's say. And here this is called BR. Okay, so this is basically SPR. This is the SPR, the complex version. This is all complexified, right? So the complex version of it. Then you can take the real subspaces. And then here BR, which is the SO2R plus 1. So odd SO2R. These are denoted as DR, and these are SO2R. So there's a big difference between SO2R plus 1 and SO2R. The Ricotta diagram already shows it's very different. Here you see all the roots have the same length. Right? All the simple roots have the same length. Here it's not the case. BR is not. And then that's of course then the single chain there's no problem at all. I mean single lines. Which diagrams contains only single lines and no cycles. No? This is the AR and this is the SUR plus 1, which is the same as SL. Because it's the complex version, so it's not the complexified level. SL R plus 1. Same thing. So this, so you see there are four series which are kind of infinite, right? Because this R can be as large as you wish. There's no restriction on that. Right? A, B, C, and D. And these are exactly the classical algebras that we already have seen, right? SU, SO, these two are SO, and that is SP. These are the classical algebras that we already knew from classical symmetry groups from a long time back, right? But these were the new ones, G2, F4, but you see there's no range here. This is a very fixed, it's only for rank 2. This is only for rank 4. And then there is also there are a few special ones. You see this thing, what we did, we started with this thing and then we started extending one side. You can ask what happens if I extend simultaneously this and another side. It turns out that's not in general possible. Only in some special cases it's possible. And the way it works is, so you can have, for example here, this is one possibility, or you can have, you can add one more, let's say one more line here, one more line here, and finally, let's see, that's it. So this is has 6 points, so this is rank 6, E6, this is E7, and this is E8. That's a complete classification. This is a complete classification of all the simple Lie algebras.
What's the formal way of determining if the geometry is possible or not? Because sometimes I can't visualize, for example, if I have 4 roots or 5 roots.
Yeah, I mean, so the way, I mean, you can, this is not covered in this, but if you take some of the textbooks which involve discussion about the Lincoln diagrams, basically by ruling out, they start by ruling out various possibilities, like cycles, you rule out cycles, or you rule out, I mean, looking at this thing, what is a possibility? Can I add some line here? You rule out that. Here, you rule out the possibility of putting something more here. I mean, this is okay. You show that there is no contradiction with that, and that is not too difficult because essentially you kind of prove that here, if I add some another point, it doesn't create any problem. No, it does not come to any contradiction if you add another point on one direction. But here, if you add another point, it is not. You can prove that it is not. It's not too difficult. I mean, because it's only 5 points. It's not too difficult.
But 5 points to be drawn have to be drawn in 5 dimensional space.
Yeah, but you can. You can. Yeah, I mean, so I mean, let's see. This is 5. Okay, we could. I mean, okay. I mean, I just give you a hint, and then I will not go through because it will take some time. So let's say. So let me label alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay. So without losing generality, I can choose, and as I said, length doesn't matter. What is really important is the angle. So I can just assume, forget about the fact that these lengths are not the same. It's not important. What we are saying is it's simply impossible to draw a diagram with these angles between any vectors. So say choose alpha 1 equal to 1, 0, 0, 0, 0. Right? I can always point alpha 1 in the x1 direction, first direction. Then alpha 2, I can choose in the first plane. But I know that dot product must be minus half, no? So that will tell you that, so let's call it x and 1, and 0, 0, 0. I choose a vector like this, and then I demand that this dot product is, not angle is minus 120. So the angle will be the dot product alpha 1 dot alpha 2, so which is x let me put here minus, because anyway dot product is going to be minus. So minus x, so x is positive. Minus x divided by the length of alpha 1 times length of alpha 2. That will be the cosine. And that's supposed to be equal to minus half, because 120 degrees, right? Now alpha 1 length I've chosen to be 1, so I can forget that. But alpha 2 is 1 plus x squared, square root, right? I'm thinking of Euclidean, this is Euclidean, all the directions perpendicular to each other. So it becomes minus, so that means, so okay, minus minus cancels, so we find 4x squared equal to 1 plus x squared, taking the square of both sides. Multiply this, multiply that there, and take the square on both sides. So you get 4x squared equal, so x squared equal to 1/3, so x is 1 over root 3, so it's 1 over root 3. Now write down alpha 2, alpha 3. Alpha 3, so which one we are looking at? This one, right? Alpha 3 has, again, it should be orthogonal to alpha 1. So the first entry is 0. It should be orthogonal. And second entry, again, call it minus x and 1 here. Okay. Fix the x now. Now this x will not be more than 1 over root 3, because you see this length is not 1. So it will be minus x divided by length of that, which is root 4 over 3, right? And here length is square root of x squared plus 1, and that's supposed to be equal to minus half, right? So you can calculate x, so whatever the number is, okay, you substitute that, let's call it x3, okay, this value. Then you go to alpha 4, so it will require some work, but still is not, you don't have to visualize in geometry, I mean picture you cannot visualize. No? So now you see alpha 4 is orthogonal to both alpha 1 and alpha 2, because there's no line connecting them. So the first two entries are 0, right? But it is 135 degrees with respect to alpha 3. So let's say call this now some minus x4, and again 1 here and 0, and you fix it that this dot product, I mean the angle between these two. So x3 we have already determined, right? I mean we've already determined from the previous condition. Now I determine x4 by requiring the angle between these two is 135 degrees, right? So here, I mean here, so it will be minus x4, the dot product, times the length divided by length, which is square root of 1 plus x3 square and square root of 1 plus x4 square, where this I already know from the previous calculation, right? And that's supposed to be equal to minus 1 over root 2, because it's 135 degrees. No? So then you determine x4 from this equation. And then finally alpha 5. Alpha 5 is orthogonal to all these three, and it has 120 degrees with respect to alpha 4. So since it is orthogonal to all these three, so alpha 3 will have 0, 0, 0. Okay. And then some, I don't know, let's call it minus x5 and something here, which we don't know, let me call it y. And again require now, so now I already know x3 and x4, right? The dot product of this is this with that, so minus x5, length of that is square root of 1 plus x4 square, and this is y squared, x squared. And you find, when you set that equal to minus half, because angle is 120 degrees, the only solution of that will be y equal to 0. No? Only solution will be y equal to 0 there. But that means this is 0, so this is still, so all of this span only 4-dimensional space rather than 5-dimensional space. So, and sometimes, okay, I don't remember whether you get any solution at all or not. But if you do get a solution, it happens to be 0. And sometimes you don't even get any solution. You find a contradiction. You simply cannot get that. Yeah? Because these lengths are such, I mean those lengths are such that then it is simply not possible. So this way you can prove. So what that is showing is that those angles are simply not possible to realize in a 5-dimensional space, which are linearly independent.
If there is an S6 and S7, can you write a E1, E2, E2B?
Sorry, repeat that again?
If there is an E6 and 7 and 8, can you write an E1 and E2?
Well, I mean, E1, E2, well, I mean, in some sense, you say, So this part of the picture is the same, right, for all these three. Then you can say that, well, I will consider this chain now. So for example, if I have nothing here, that is nothing else but A4, right? So if you wish, I can call that as E4, but E4 is the same as A4, because if I remove these 2 points, right? Now if I look at if I remove only 1 point, but that is the same as B4, right? Because this picture is the same as that picture with the R equal to 4. So E5 is the same as D4. So normally we don't call E4 and E5 because that's already part of the series. No? But if you wish, you can call it also. Because the E series has something to do with the fact that there is this part and then I extend here on this side. No? So we have this and E8. And once again, you can prove that if I put one more line here, is not possible. This is of course that requires now you have to go through 9. You have to go through this. But you prove that one can show that it's impossible. I think it's not even a question of linear dependence. I think it was impossible. Okay. Yeah. Or similarly, this side you cannot draw. I mean, this side for any of this diagram, you cannot have a situation. Okay, this diagram, yes, you can draw on this side. But if you have 3 here and 3 there, again, that's not possible. So that is the power of this thing. That I mean, so we just started completely abstractly from the Lie algebras. Let's say semi-simple Lie algebra. We arrived at this, and we used repeatedly the Cartan-Killing form is non-degenerate, and that gave us enormous amount of information. No, and finally we were able to show that if you specify this Aij, the Cartan-Killing matrix, you know completely the Lie algebra, right? And the Cartan-Killing matrix is, Cartan matrix is, can be diagrammatically described in terms of Dickin diagrams. It's much easier than staring at that 2 by 2 matrix with different entries. You know, those numbers do not end. I mean, you cannot visualize anything with those numbers. No? But when you draw a diagram like that, the meaning is very clear. And then the whole problem of whether it exists or not is the issue of whether geometrically you can realize this. Geometrically you can realize this, these different angles in the Euclidean space. Euclidean because we already shown it's positive definite. In the HR, restricted to HR is all positive definite. So you can just work with the Euclidean space.
When you have the X product between 2 groups, how would you look at in the Dickin diagram?
If you have what?
The direct product between two groups.
Yeah.
For example,
semi-direct sum of direct sum of Lie algebras. Yeah, it will be 2 disconnected graphs. I mean, so for example, if I take SU3 times SU3 at the level of group, this is the level of group, direct product. But at the level of algebra, it just becomes the sum SU3, direct sum SU3. Right? In that case, SU3 Dickin diagram is the A series A2, right? So this is A2. So there will be this here, and there is no connection between these 2. So direct sums are like that. So when we have 2 disconnected Dickin diagrams, I mean, in a big Dickin diagram there are 2 disconnected pieces. Those are direct sums. Those are not simple algebra. Just semi-simple. What would you like? I mean, let's see. I mean, we have. So let's look at all the rank 2 cases. By the way, this is what you should. Chapter 13. From chapter 13, you will, if you go to the chapter 13, which discusses the classical algebras and the roots, constructs all the roots, and then from there you can deduce what are the simple roots. Simple roots are described again in chapter 14 for all the classical algebras. But already from chapter 13, you yourself can do it. No, you don't have to look at chapter 14. But no, what are the simple roots? To really show, because I just said it. No? that this diagram, this kind of diagrams are SU, no? But you can explicitly show it from this. You can show that these are the SU algebras, these are the SO odd algebras, and these are the SO even, and that's a separate. So that's why you should really go through chapter 13. I don't have time now to, because that will require, it's a lot of messy calculation, no? But conceptually there's nothing different, new. It's all just a messy calculation. So please go through chapter 13 to convince yourself that these are indeed this infinite series because R is unbounded here. No? These infinite series correspond to our classical algebras, right? SU, SP, SO. Whereas these were the only five exceptional cases, and they don't have any infinite range. Those are just for specific rank. Now, just to give an example now of, should I do that? Okay. Before I go into an example, let me also mention how do you construct irreducible representations of this. You remember for SU2, what SU2 is what? SU2 is A1, right? SU2 R equal to 1, A1. SU2 is just one dot. That's it. Right? That's SU2. And how did we specify what do you call the? So remember this SU2 was you had this two roots. The kata, this was, let's call it alpha and minus alpha. Two roots.
SU2 is similar dot in R diagram that made of similar dot. That's why you see SU2 everywhere.
That is why? Yeah. Every dot. Yeah. Every dot represents an SU2 subalgebra. Yeah. Every dot. Yeah. So this is SU2. And how did we specify? We just specified by giving the highest weight state, right? So the highest weight state will be some weight. So it just so I can just specify it by giving the number 2j. Because remember, we have normalized, we have doubled, we are working with sigma 3, not sigma 3 by 2, right? We have multiplied by 2, so that everything is, we never have to deal with half integers, it's all integers. So if you specify this integer, any non-negative integer, for every non-negative integer there is an irreducible representation, right? With the corresponding quantum numbers, the J3 quantum number. J3 is this H alpha. H alpha is the J3, right? J3 is the SU2, and that will be the highest eigenvalue. And then when you start applying lowering operator, right, you get the complete representation. Exactly the same thing works for any of these diagrams. Okay, you just randomly choose for every dot. You choose some numbers, let's say n1, n2, n3 integers, and non-negative integers. Okay. So these are all ni's are non-negative, are greater than or equal to 0. It could be 0, but okay. For every such choice, there exists a irreducible representation. That's the idea. Because what it is saying is that when you specify this number, we are saying that this is the highest weight state. Okay. But highest weight is with respect to all the, you see, what are we saying? We want to take all of this x alpha I are the simple roots, and simple roots, okay, so these are positive roots in particular, and simple roots are providing a basis for the positive roots. So x alpha I in some representation, we have the highest weight, this is equal to 0 for all alpha I. Simple roots. Okay. So we are considering such a state, and then we start applying all the x minus alpha i's. Okay. Just like we were doing for SU3. Remember for SU3 we had alpha 1 and alpha 2, and we choose 1 0, which gave you fundamental representation. 0 1 gave you anti-fundamental representation. Right. 1 1 was adjoint itself. So that's the idea. So you this will specify the highest weight, and then you start applying x minus alpha I to construct all. Notice that even though I'm demanding only that this is the highest weight with respect to these simple roots, this is true for any positive root. because any positive group can be written as sums of these x alpha. For example, let's say if I look at, suppose alpha 1 plus alpha 2 was a root. Huh? Okay. Suppose it was a root. I mean, it need not be, depends on the kinds of algebra you're talking about. Suppose this was a root. Okay. Then I know that x alpha 1 plus alpha 2, I can write, it will appear in the commutator x alpha 1, x alpha 2 with some non-zero number. Right? So if I apply now x alpha 1 plus alpha 2, I mean r of x alpha 1 plus alpha 2, that's the same as applying the commutator of r x alpha 1 and r x alpha 2 on SW. But since each of them annihilates it, it tells you that all the positive roots annihilate it. So this is a simultaneous highest weight with respect to all the positive roots. Okay? And then you go through the procedure to construct all the remaining weights, and that gives you an irreducible representation. Of course, it's going to be much more complicated to work it out. Already we saw in SU3 how complicated it was, despite the fact that we could draw it on a plane. It was, multiplicity issues and so on and so forth. But the principle is this. This is the basic principle. From here you start.
If you see the DR series, and you can see the DR series, the number of points is R, right?
Yeah.
So, but we can easily see that if R is equal to 2, then the shape would not be like that. It would be like the SU2 and the SU2. That's why the SU2 is a double cover of
SU2. Let me see here. You see. In this, there is no concept. You see that what's the difference? You need a bifurcation. There is a bifurcation.
I'm just saying that if suppose that R is equal to 2, then we cannot have that 3-point word.
Yeah, exactly.
Then
so
that's why the SO2 is a double cover of SO4, because it just looks like
SO3. SU2 is double cover SO3.
Yes, sorry, SO3.
Yeah. So SO3 would be, SO3 is just 1 point. So you see this again, exactly, you're right. Here it has no sense of writing B1, no? Because, for a diagram like this, you need at least 2 points. No? So these are very special cases. B1 would be what you call SO3. Right. But, the issue of double cover, etc., you don't see from the Dinkin diagram. So this is the level of purely algebra. No?
But we can see that it's something connecting SO3 and SO2, because when the diagram for SO3 is not the generic kind of diagram for SO outward plus 1.
Yeah.
And the same goes for the DR series. If we put R equal to 2, then SO4 is kind of like SO2 cross SO4.
SO4, in this case, it's like removing all of that, right? This is SO2N, SO2R. So if you remove all of that, then you are this line is not connected. This is not connected to that. So we just get two dots, no? So which is SU2 cross SU2. That's not a simple algebra. That's a semi-simple, not simple. It's a direct sum of two SU2s. But the global information you don't get. From this. This is purely algebra. Okay. This is the way you construct. But the computation about this starts becoming, of course, very difficult to construct all the weights beyond rank 2. Rank 2, in principle, one could do. And there's one nice thing that you see. But incidentally, let us just try to. So in the SUN, just to illustrate some examples. So that if I take SU R plus 1, okay, so there are R points here, so SU R plus 1. If you take the representation which is say 1, 0, 0, 0, 0, because we said any non-negative integers, so this would correspond to the fundamental representation. Okay, it depends on your definition. Whereas if you take the 0, 0, 0, 0, last one here, that will be the anti-fundamental. Just like in SU3, 1, 0 was fundamental, 0, 1 was the anti-opposite complex conjugate of that. And the adjoint representation is given by 1, everything 0, 0, 0, and 1.
The last one.
In the SO2R, in even dimensions, I don't know if you have in the RQM, have you done this concept of chirality?
Yeah.
You're done. Oh, good. So SO3,1, which is even dimension. It doesn't matter. Signature is not important. Whether it's 3,1 or 4, in both cases you will have chirality. There's a concept of gamma 1 plus gamma 5, 1 minus gamma 5 projection. And this is true for all even dimensions. In odd dimensions, no, it is not. There is no concept of chirality. But in even dimension, there is a concept of chirality. And the way it works out is that if I draw this diagram, and if I put 1 and everything else 0 here, then this corresponds to the fundamental representation of the SO. What is a fundamental representation? Vector representation, right? Because SO2n, this is SO2R. We realize it as a 2R by 2R matrix, right? 2R by 2R anti-symmetric matrices. SO2R Lie algebra. We are always talking about Lie algebra. So this is acting on a 2R dimensional column vector. But that is really the vector in 2R dimensional space, right? So this is what is called the vector representation. And its dimension will be simply 2R. On the other hand, if you take this diagram, I mean, if you again take the same Deakin diagram, but put here everything 0, I mean 0 here, all the numbers 0, but here you put 1 and 0 here. Okay. That representation turns out to be the spinor representation. Okay. SO2R, the spinor. Maybe that is what I should do. So this gives you a spinor representation, but a definite chirality, right? So let's say positive chirality. I mean, according to some convention, say it's positive chirality. Then the other guy, so let's say this is a positive chirality. Positive or negative depends on the definition. Important thing is the relative part. Positive chirality. Then the negative chirality is obtained by taking 0 here and 1 here. There is a symmetry here, you can see. I mean, you can exchange. This diagram doesn't change when you exchange. So these are the two things. Generally speaking, the vector representation and the spinor representations are very different dimensions, right? So vector representation was 2R dimensional, but the spinor representation goes like 2 to the power of R, 2 to the power, so it's exponentially grows in R, with R. Yeah? So, for example, in 4 dimension, 2 to the R, SO4, which is the same as 2R, R is 2. So 2 to the 2 is 4. So yeah, but that is the total spinor, total Dirac spinor. So each of these dimension is 2 to the power of R minus 1. Okay, 2 to the R is the total dimension of the full Dirac spinor, and which includes both chiralities. So once you divide by into chiral, it will become half of that. No? So 2 to the R minus 1. So in general, you see that this is very large. I mean, if you take, for example, if I take SO10, which is what appears in string theory, for example, 10-dimensional theory, vector representation is 10-dimensional. But spinor representation is 2 to the 5, I mean, in the full spinor, Dirac spinor, 2 to the 5, which is 32, which splits into 16 plus 16, 16 left and 16 right. You know, it's so it's clear it keeps growing rapidly as you increase R. This dimensions increase rapidly. But a very special case happens for SO8. If you take SO8, there's something very special happens, because you have now rank is 4, so it is just this diagram. This has a peculiar symmetry, you see. Before we said this, generically we have a symmetry, we can just exchange these two, right? Now here, so remember this was like the spinor, this is the vector, and this is the spinor prime. I mean, when this notation means 1, 0, 0, 0 means spinor, 1, 0, 0, 0 means spinor prime. Spinor prime is opposite chirality. Positive, they say this positive chirality and negative chirality. And by V I mean 0, 0, 0, 1. those numbers, those integers, Ni. So these are three different representations. But this is just to indicate from where the vector comes, from where the spinor comes. Now this is an amazing thing that there is of course this symmetry exchanging, but I could also exchange these two, right? So I could exchange vector with spinor. Okay. And keep spinor prime remain the same, nothing happens, right? I mean, if I do that, nothing happens there. Or I could exchange these two. So vector is spinor prime and spinor remains spinor. So there are lots of, this is what is called SO8 triadity. SO8 triadity. And in particular, you see, why is it possible? Well, I mean, if we are saying that this is possible, we better check the dimensions. If the dimensions are different, there is no sense, right? You cannot. But indeed, SO8, this SO8, the vector is 8-dimensional. Dimension of vector is 8. A dimension of the spinors is 2 to the power of r minus 1. So r is 4, 2 to the 3, which is 8 again. So it's an amazing fact that this is everything dimension of, this is the same as dimension of spinor is the same as dimension of spinor prime. Spinor prime, these are two characters. It's a very peculiar feature of SO8. It doesn't happen in any other dimension. And essentially the superstrings exist because of the triality. Exists logically. I'm not talking about in real world whether it exists or not. In a mathematical sense, it is a consistent and entirely due to this fact, SO8 triality. The spinors are like fermions, and this kind of tells you there's a symmetry between bosons and vectors, fermions. That is what comes out. SO8. Now, what should I do? I have two choices now. Either I go through just the rank 2, in particular construction of all the roots, given this diagram. Rank 2, I have a G2, I have a A2. A2 we already know, it's SU3. And then we have B2. B2 and C2, there's no difference, right? Because if R is 2, this disappears, then I have just these 2 points left. It doesn't matter which one is the longer, which one is shorter. But once you attach other points, then it makes a difference. No? But at the level of, for R equal to 2, both are the same. Which basically means SP2 is the same as SO5 at the level of Lie algebra. At the complexified. We are always thinking in terms of complexified Lie algebra. So this is, those are coincidences. So either I describe this construction, or but this is given in the notes. I mean, maybe should I just ask you to request you to read that yourself? I think so. Yeah, this is section 14.4. It goes through the just step-by-step construction. Given the simple roots, you start construct alpha 1 plus alpha 2. Is it possible or not? If it is possible, you have another point. This way, systematically, you construct all the roots. So the whole 14.4. So I mean, just to, I will just give state the final answer, but you have to check it. So SU3. So we are taking R equal to 2 case. So we have the possibilities of so B2 which is equal to C2. That is nothing. And then you have A2. What else? This okay, let's call it D2. But D2, you see, D2 is really forget. I mean, yeah, D2 is really not. Why shouldn't D2 is nothing else but A1 plus A1, right? Because if I remove all of these points, then these 2 points are just remaining there with no connection. So it's A1 plus A1. So that we don't need to worry about. And then finally G2. A2 is SU3, and that root system we have already worked out. So we had this alpha 1, alpha 2. That was this picture with the angle 120 degrees, which was that A2, right? 120 degrees. SU3. SU3, sorry, SU3. Yeah, SU3. Okay. So alpha 1, alpha 2. And when we showed that, and then from that information, we already know that this is a doublet. This is part of the doublet with respect to alpha 1, and this is part of the doublet with respect to that, right? From those numbers, -1. So that means there is this here, and there is this here. So there is this. So these were the roots, all the roots. SU3. D2, okay, D2 is simply, if I draw, it will be simply this. It will be perpendicular. Because these two alpha 1 and alpha 2 are not connected in the D2. So they're orthogonal to each other. So it's just that. So this is just one SU2 here and another SU2 here, and they don't talk to each other. They commute with each other completely. So this is trivial. B2 on the other hand, what happens is basically this diagram. So this would have been the case for this is basically SO4. SO4 is the same as SU2 plus SU2. Okay? But SO5, this is B2 is SO5, right? And this is SO4, which is equal to SU2 plus SU2. The algebra. SO5, SO4 is certainly contained inside SO5, right? So you have, of course, these roots, but you have more roots. And in fact, one can show that the roots are just this here. I think that is extra roots. So, I think so. Those are the roots. And now it's rather non-trivial. This is this you cannot separate into two, which is clear already from this diagram. This diagram, this was this diagram, right? This diagram is not disconnected. So this is G2 is rather interesting. G2 is the only one which consists 3 lines. That's the only thing. From this side, there's nothing else. G2 is like taking this SU3 picture here. SU3 picture. But then, see, the angle between these two is 150, right? This angle is 120. So the alpha 1, if alpha 1 is here, then alpha 2 should be somewhere here, right? This is 30 degrees. That's 150. And not only that, its length square is 3 times that length square. So we said that this must be a spin 3/2 with respect to this alpha 1, right? So we will have, maybe, I don't know, I'm drawing correctly. So maybe this is not really something like that here. So then there will be a point here. You add this alpha 2, this alpha 2 plus alpha 1, and then there will be alpha 2 plus 2 alpha 1, and then alpha 2 plus 3 alpha 1. Right? This is spin 3/2 representation. It will go there. And if you look at this one here, if you consider alpha 2 string passing through alpha 1, okay. So then you see you find that this is a doublet with respect to that. Okay. That's because remember there's a 2 alpha 1 alpha 2 over alpha 1 square was -3, and 2 alpha 1 alpha 2 over alpha 2 square is -1. So the P and Q are different, right? Because this length is 3 times that, length square is 3 times that. So this is -1. So if you consider the alpha 2, SU2 coming from alpha 2, and ask the question, what does alpha 1 represent? This must be spin 1/2. Okay. So this, which is just that, which is, I think this should be parallel. Yeah, this should be that. So this forms a doublet, and you keep going, and you find, you have to construct from the various things here. So, for example, you ask the question here, this one, not this one. anyway, I mean, I will not go through the whole detail, but it is described, it's explained in this notes, that at the end you find that you have these roots, which are the original SU3 roots, right? And then you have this root here, alpha 2, and here, these are all equal, the length square 3 times rho small length square. This is, you see, this again 30 degrees, and then the negative roots of that. It's a little bit of work, but I really don't have time for this. So it's a very nice, shape. If you try to draw this, this becomes a star. You see. Yeah, it's a star shaped. It's a really star shaped root diagram for G2. This is the only thing which involves 3. Okay, now this is now. Should I discuss the spinor representation, which is not part of this?
In 5 minutes? Or
5 minutes?
10?
10 minutes maybe, okay.
What kind of shape does E8 make? 240 points.
First of all, you are drawing 8 dimension. 8 dimension. The dimension of E8 turns out to be 248. The dimension of this group, or Lie algebra, is 248. 248. Now I don't remember the dimensions of this. I think it's, I'm not sure, maybe 133? No, I'm not sure. I don't remember the numbers now. Anyway, so this is 248. I remember. 248. 56 times 2. Yeah, I can, okay, 56. 56 times 2 plus 3, what is that? 56 times 2 is 112. 112 plus 3, 115. Yeah, just 248, so 133 indeed. 133 dimension of that. And E6, I think, is 27. I mean, okay, I don't remember, 56 maybe, or 78, something like that. Okay, there's some dimension. So now.
How do you see that?
Huh?
How do you count the dimensionality?
No, this is the I mean, this I mean, I know the result. That's why. I mean, it's not that. I mean, because to get that, you need to construct all the roots, right?
Ah, okay.
That is that's.
So you remember it, just
because this appears in string theory so much that
248 is a very famous number.
248 is very. I mean, again, just like the SO8 plays an important role for the, but E8 plays an important role because that appears in this string theory.
in the dot string theory.
Yeah, not string theory.
So were the roots of E8 first done by hand or by computer? Who was the person who did all the roots of E8 because there are too many roots?
Yeah, I mean, I can. I can write down the. I can write down the roots. Yes, I can write down the roots in a Euclidean basis. Yeah. So, but before that, so what happens is that let's look at the SO2ns. SO2ns. You can write the roots, and so n is a rank. Maybe I should call R. R is a rank. So that means I should be everything I can write in an R-dimensional Euclidean space, right? The roots I can put it in the Euclidean space. All the answer. It turns out that this is simply choosing. So put everything 0 except 2 entries. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let me put here 1, 0. And plus minus 1, plus minus 1. And these positions can be anywhere. Okay. That is the adjoint representation of the SO8. So this gives you non-zero roots. We can count how many are there. See, first of all, you have to choose 2 positions out of 8, right? So you have 8C2 possibilities, and every time you have 4, right? Because plus minus. So 4, 8C2, and what is 8C2? That's so 4 times 8, 7 over 2, which is 112, right? 112. So 112 non-zero roots, and kata is 8, right? 8 dimensional. SO16. We are counting SO16. We are talking about SO16. SO16. So that's plus the kata, a total dimension. So this is non-zero roots. Non-zero roots. And then there are this 8 kata. So total dimension is kata. Kata 160. 116, sorry. 120. 112 plus 8. Which is the dimension of SO16, right? 16 times 15 divided by 2. That's the dimension. Right, this is a general feature for any SO2R. You just have R points here, right? So this time it will become RC2, 4RC2. So 4 times R minus 1 over 2. So 2R times 2R times R minus 1 plus the rank plus R. Plus the rank is R. And that should, if you have not made a mistake, it should be the correct dimension. So this is the right. This is the whereas vector representation. So this is the adjoint representation. Now, if you look at the vector representation, it is the same thing but only one entry. So R minus 1 of them 0, and only one entry is plus or minus 1. Okay. How many ways are it? You have R possibilities. For each of them, you have 2 possibilities here, plus minus sign. So 2R dimension. So vector representation is 2R dimensional for SO2R. Right? SO2R acts on a 2R dimensional vector space. That's it. Spinor, that is the thing. So spinor, on the other hand, spinors are given by so half. So again, plus minus half, all the entries plus minus half. Simultaneously, nothing is 0 here. So this is spinor. Okay. Where the difference between spinor and spinor prime is the choice of plus and minus. So for the spinor, say you choose the even number of minus, or in other words, sum of these numbers, let's call this weights W1, W2, WR. You say the sum over WI is equal to even number. Basically what I'm saying is, maybe I don't have to write that. Just say even number of minus signs or odd number of minus signs. Okay. So spinor or spinor prime. So SP or SP prime, you would distinguish it by saying that there are even number of negative signs here, and here you say odd number of negative signs here. That is
it means that we have freedom to choose R minus 1 of them, and the last one is determined. Can we say that?
Yeah.
So that's why the dimension is 2 to the power R minus 1.
Yeah, correct. Yeah, that's right. Yeah. So if you have no restriction, then you have a Dirac spinor. Both spinor and spinor prime. A Dirac spinor is 2 to the R dimension. 2 to the R dimension, Dirac spinor. But then in even dimension, you can define a concept of gamma 5, no? Which is gamma 2R plus 1. You can define a gamma 5, analog of gamma 5, such that gamma 5 square is 1. No? Then you can apply the projection operator, 1 plus gamma 5 divided by 2, 1 minus gamma 5 by 2, to separate the spinors. So that's so in particular for SO16. SO16, this dimension is, if I take one of them, just one of them, will be 2 to the power of 7, right? 2 to the 7 is how much? 128. 128. Okay. Now what is nice about this is that the E8 has a maximal, there's a concept of maximal subalgebras. So each of these groups have, each of these algebras have lots of different subalgebras, right? Not the ideals. The simple algebra has no ideals. But you can still have lots of subalgebras, right? The maximal subalgebra is the one which has the same rank as the original algebra. Okay? Because to that you cannot add anything more, right? I mean, that's the maximum. So it turns out that SO16 is contained in E8. And is the maximum because both are rank 8. So what this means is that the adjoint representation of E8, I can try to understand it in terms of representations of SO16, right? So how it splits the adjoint of E8, which is 248 dimensional. This splits into adjoint of SO16, which is 120 dimensional. That's adjoint. Plus the spinor of SO16. Spinor, you can have a chart, either spinor or spinor prime, doesn't matter. So let's choose one of them, and that's 128. So this is the way. Actually, that's the easiest way to understand E8. I mean, I find it much easier. When I think of E8, I think always of SO16 and decompose in terms of the spinor and adjoint representation. Now, what I wanted to really prove, I don't think I can do it, but what I wanted to prove was this formula. The dimension is 2 to the r. The Dirac spinor will have a dimension 2 to the r. If I add the two things, it will be 2 to the r. So this is what I wanted to prove. I don't know.
In the RPM course, he said yesterday that today you will teach us about higher dimensions.
Cool. He said that?
Yeah.
Good. Then okay.
So we will prove it.
Okay. Yeah. Basically, by using a totally different technique from what we have been doing here so far, it is to write the gamma. You have gamma matrix algebra, right? That is what defines the spinor, right? So gamma matrix algebra, and but you do a little trick here. You split the gamma matrices in terms of a kind of half of them creation-like operators and half of them annihilation-like operators. You can do that always, by going to the complex, say gamma 1 plus I gamma 2, gamma 1 minus I gamma 2. These combinations you can split into creation and annihilation, and then you apply the creation operators, and you find that the dimension is 2 to the r. Yeah. So if he is doing that, it's okay. All right, so I think.
What about the process you were going to do?
Sorry?
For bringing this to there, what were you going to do?
Yeah, that's exactly. And if Eddie is going to do it, then I don't need to do it. I mean, it's good to sort of know what is the. Because, okay, you're done 4-dimensional gamma mu matrices, right? And you saw that it is 4 by 4 matrices. So the idea was to check what is the.
I think in the higher dimensions, we wrote them by
Yeah, I mean, that maybe, it doesn't matter. That's just a notation. Capital gamma, That is sometimes usually distinguished between the 4-dimension. Because normally when we talk about higher dimension in physics, we think of, like at the end, we want to come down to 4-dimension. Right? Which means, like string theory is supposed to be 10-dimensional, right? What we mean is that the remaining 6 dimensions have some very compact, small size space. That is why we have not been able to observe them yet, because they are too tiny. So that is just to distinguish between the big 10-dimensional space and what is 4-dimensional space. That one uses capital and small gamma.
Because in string theory, because it is written capital gamma matrices.
Yeah. Right. So many things I have not been able to do. There are actually many things, yeah. But I hope you will read the 13th chapter to at least see the Deakin diagrams, the infinite series are the same as the classical Lie algebras.
So the exam is all the 14 chapters.
Yeah, all the 14 chapters. Yeah, 13. I mean, okay. I think for this Friday, it's tomorrow. Tomorrow you don't do the exercises of 13. Okay. Do the others which I have covered. I mean, I don't know. 11, 12, 14. I don't know if there's any. 14. There are a few things. Yeah, try to do this. I mean, try to do the 14, which is I was not able to do. I didn't have time. But you could try to. Let's see. 14 has some things, right? There's exercise 14.2. Ricotta Matrix and Lincoln diagrams. There are a few exercises in 14. I could try to do this. Ricotta Matrix. There's 14.3, 14.2, 14.3, 14.5. There are a few exercises in. I mean, you could try to do this. Although I was not able to go through it, but things are explained in the lecture notes. So, I mean, what I didn't go through is how, given the simple roots, how to construct the remaining roots. That is why I wanted to do the G2, because G2 is the most complicated among the rank 2. No? So if you have understood G2, then you understood everything. But don't have time. So try to do, but 13 has a lot of exercises, and maybe you can submit it the next week when you meet. Next week there will be a tutorial before the exam. So probably it's on Wednesday. Thursday is the exam? Thursday's exam? Yeah. Thursday's exam. So probably the tutorial will be on Wednesday.
So for this Friday, only 11 and 12.
11, 12, and try 14th if you can do.
Okay, everything.
See how far you can proceed in the 14th. I will not insist on 14 because I really didn't cover the 14th chapter. That particularly that part. But though all those exercises which are not to do with the construction of all the roots, no, that you could try. I mean, that is there. Like, I think one of the questions was the Ricotta matrix. Show that the Ricotta matrix is this for some algebra. No, that you could do. Yeah, I think this course requires if I wanted to cover all this, I require maybe 20-24 lectures, which is what it used to be in the old times. Now they reduce it.